have to, in some sense, work through the derivation of the gradient and run it on a data set you've already seen before. So that should be a little less effort than earlier. Also because you've already written that kind of code. If you feel particularly you don't want to write something from scratch, my suggestion is take your SVM code and change the contents of the innermost for loop to be the gradient that you derive, and that's literally it. If your SVM code works, your logistic regression will work. Any questions about the homework? I noticed there's some discussion on the discussion board, but are there any pressing concerns that you would like to get resolved?
I have a small question. On 1.3,
Okay.
where it says let n be the number at the top of a fair six-sided die, and then if a fair coin is tossed n times, what's the probability of exactly 2 heads? And on the discussion board, there were some people talking about it and saying that well, basically my question is, should the answer be something that depends on n?
No, of course not. N is just the number that shows up on top, so you can't.
Okay, so it's not saying we roll the die and you have this n and now
No.
use that to do this?
No.
Okay,
The answer should be independent of N.
okay.
Yes. Other questions? And in some sense, these probability questions should be familiar to you even before you started ML class, because these are the kinds of things that you see in Intro to Probability class. So it's mostly to just bring this stuff back to memory. Projects, I'm still working through your intermediate reports. It turns out reading 90 reports is more time consuming than I had originally anticipated. But I'm hoping that you should all get your feedback by quite soon actually. Please continue working in the meantime. The reports are currently due on December 8th, that's next Friday or Thursday or something like that. And a couple of people asked me if I could push the date back into exams week. Any thoughts on that? You say yes now, but here's the problem. Many of you have many exams. So it will end up crowding your exams week a lot more. The reason I had it early on, before the exam week, was so that you could get it done and then study for exams. But the argument that was made was, it doesn't matter if it's pushed back, I might end up submitting before anyway. I guarantee that's not going to happen. The deadline means something special. But if there is agreement that you want to push it back, I'll just keep this conversation open for another day. And if you have any thoughts, please post something on the message board and I'll probably make a change or not, depending on what you guys think. Yesterday I noticed that in the competitive project, someone crossed 90, which is pretty cool. That tells you that interesting things are possible, so please spend some time on that if you're doing that. The other thing that I wanted to bring up is the final exam. There's going to be a final exam in class. It's on the 14th of December, that's a Wednesday, and it's at 8 a.m. And I assure you I did not pick the time. It's at 8 a.m., it will be in class, it will look a bit like a midterm. We cover everything that we did from learning theory, basically. Okay? Any questions about any of these things?
I have one more about the homework.
Do you have homework?
I just have an exam question.
Let's get to homework and then get to it. Yeah.
In the Naïve Bayes one, part A, it says if we have infinite data drawn from this distribution, what would the probabilities be? Isn't it? I mean,
The most obvious answer is probably correct. Think of the weak law of large numbers. The law of large numbers. You have infinite observations, you will converge to
the same.
Yeah.
Okay.
It's not a trick
It just
question.
seemed like a trick question.
No, it's not.
Okay.
So you said the exam starts from the programming theories was at one, like it's not comprehensive.
It's not comprehensive. It is everything that we did not cover for the winter. So that's it. The nature of the class is that we do use things from before. So for example, we covered linear classifiers in the first part of the semester. We covered the expressivity of linear classifiers in the first part of the semester. We cannot really go do too much in, say, SVM without reasoning about the expressivity of linear classifiers. So it's not like those things cannot exist. It's just that the focus will be more on the new stuff. Okay? Yes?
So you mentioned that in order to get the project due date pushed back, we need to post something?
No. Okay, I was obviously not very concrete on something. If you have an objection to pushing back the project deadline, please post a message. And if you don't feel good about posting an objection in public, send me an email. Okay? In the absence of any information, I might end up pushing the project deadline. Most likely what I will do is I'll put it in the middle of exam week. At the end is a problem actually. The end of the exam week is actually an interesting issue. A non-trivial fraction of this class goes to the algorithms class, and the algorithms final is the last day of the exam. So I'm not sure. I mean, does anyone have issues if I push the project deadline to the absolute last day of the exams? You have a problem?
Oh, no, I'm just going to say I think one of the concerns is the algorithms project is actually due like that day or the day after. So I think the concern is just having some wiggle room in writing our papers, not having the project done.
Sure.
Because we'll be writing a paper in that class as well.
Right. So which is why a weekend, for example, would be hopefully enough. But you want it to the end of the... I'll think about this and I'll probably push it back unless someone has concerns. And if you have any opinions, please voice it. So duly noted with your points. Any other thoughts?
Push it to the week after time.
Why not next semester?
Yes.
Great idea.
That's good.
You guys are actually doing good stuff on the projects, I must say. The intermediate reports are kind of entertaining, a lot of very cool stuff, so I do want to see the end of that. And it's actually, I'm not kidding, my favorite part of this class is the project because it's the part where I get to learn stuff. Not saying that I don't learn stuff by teaching, because every time I teach, every semester I've taught this class, I've learned something new about one of my own lectures. Because, just the questions that you guys ask makes me think about something in a different way. And the project is from out of the blue. So I end up, either learning or understanding some application or some little nuance in machine learning a lot better. So personally, I enjoy the projects part. So I hope you had fun as well with that. Let's get back to the lecture. And there's going to be a little bit of a change in the outline of the topics. So if you look at the lecture schedule today, it says learning with partial supervision, the EM algorithm. The EM algorithm is one of, it's not really an algorithm, but it's actually a recipe for generating algorithms when you do not have labeled data. And it builds upon this kind of a probabilistic classification idea. Unfortunately, I'm going to have to take at least 2 lectures to get through the details of the EM algorithm, and we just don't have the time. So I might end up having to skip this section on learning partial supervision, basically unsupervised learning, including the k-means algorithm. How many people have heard of the k-means algorithm? It turns out k-means is actually an instance of EM. It's a tweak on the EM algorithm for a certain class of probabilistic models. Again, unfortunately, I'm not able to, get enough time to cover all that material. Partly because I want to spend the next lecture talking about neural networks. At the beginning of the class, we had a survey, remember? And one of the most common requests was, can we have a lecture on neural networks? So, so I'm going to ditch the EM algorithm and bring in a lecture on neural networks. So, and also, next week's class is a good place to fit it in because logically reasonable way to move forward from where we are. We are in the middle of probabilistic models. We are actually talking about logistic regression, linear models. We'll be talking about the sigmoid function, and all these things take it to a nonlinear classifier, and you get neural networks. So there's a continuity in ideas. So if you really want to get through the EM algorithm and k-means and such things, I'm going to leave the slides up there. And you can also find last year's video if you want, and if you want, we can talk to each other. Any questions or thoughts about that? Anyone has a strong preference for EM? EM stands for expectation maximization, which is such a positive sounding thing. Alright, so on that note, let's move ahead with where we were. At the end of the last lecture, which is before Thanksgiving, I had started this lecture on logistic regression. I'm going to just go through the couple of slides again so that we have some continuity. Let's think back at the entire semester. We spent a lot of time talking about linear models. We looked at what linear classifiers are. We looked at different algorithms for learning linear classifiers, perceptron, Winnow, the support vector machines, variants of these things. We also looked at, turns out AdaBoost can also be seen as a linear classifier on top of the weak classifiers, and so on. So we have various algorithms for linear classification. We also looked at this general idea of learning as loss minimization. And I'll summarize that idea again at the end of this lecture. Okay? And throughout the semester, we've been asking the same question: what does learning mean? And different answers to this question gives us different learning algorithms. If I define learning in the form of this online learning setting, you get the perceptron and Winnow algorithms. If I define learning in the form of PAC or in the form of as loss minimization, you get SVM. If you try to reason about weak and strong classifiers, you get the AdaBoost algorithm, and so on. And most recently, we've been discussing learning in the form of from a Bayesian perspective. And under this perspective, we have two criteria for learning. One of them is the maximum a posteriori learning or map learning, and the other one is maximum likelihood estimation. That says MLE estimation, it should just be ML estimation, because E is estimation. And we looked at the Naïve Bayes classifier, which was actually which was the first classifier that we saw that predicts probabilities. And we saw how we can learn the Naïve Bayes classifier under the maximum likelihood setting. So this is roughly 20-second, maybe 1-minute summary of all the relevant parts of the entire semester. Any questions about this? At the very end of the last lecture, we saw this discussion about discriminative versus generative classifiers. Remember, a discriminative classifier is, or discriminative learning is when you learn a function that predicts the probability of the output given the input. That's discriminative learning. Generative learning is when you learn the joint probability, output, comma, input. So, a discriminative learning is when you learn P of y given x. Generative learning is when you learn P of y comma x. In some sense, in a discriminative setting, what you are saying is that I really don't care about how instances are generated. I don't care about how the x comes into existence. All I want to learn is this shape of the classifier, the shape of the decision boundary in some sense. What is the probability that the label is a certain thing, having observed a particular input? A generative classifier actually tries to learn more. In a generative setting, you want to learn not just the decision boundary, but also how the inputs are laid out. So if you have a cluster of inputs here, you have a cluster of inputs here, let's say both of them are labeled plus. A discriminative model will not care that there are two clusters of the inputs. A discriminative model will not care. A generative model tries to actually model the regularities of the data as well, of the inputs as well. And the Naïve Bayes classifier is the first and looks like the only example of a generative classifier that you will see in the semester. If you kind of squint and take a probabilistic perspective on the previous classifiers that we saw, everything that we saw so far was discriminative. Everything that we saw directly learned the decision function. We did not try to attempt to model the inputs as well. Okay? So today we look at what is called the discriminative variant of the Naïve Bayes classifier. The Naïve Bayes classifier is a generative classifier. Logistic regression, it turns out, is its discriminative variant. And I'll tell you what I mean by that. And we'll formalize the connection of logistic regression to Naïve Bayes. And so I'll spend some time talking about how we can derive the maximum likelihood and the maximum a posteriori estimates for logistic regression, and then draw the connection back to learning as loss minimization. Let's start with logistic regression. It's a familiar setting. We want to train a binary classifier. The inputs are feature vectors, d-dimensional feature vectors, and the labels are +1 and -1. And we have some training set, m examples. Each of them is a pair. Each example is a pair consisting of an example in the form of a feature vector and its label xi, yi. So it's exactly the same setting we've been using for the entire semester. And so first of all, the important thing to know is we're trying to learn a classifier. The outputs are +1 and -1. And instead of learning the classifier directly, what if we learn the probability of the label being 1? This is what we did with Naïve Bayes also, right? We learned a function that predicts probabilities. But in Naïve Bayes, we took a somewhat interesting route. What we said was P of y equals 1 given x by Bayes' rule. It's enough if we learn P of x given y and P of y, and we just learn those two functions. Instead, in logistic regression, what we're going to say is, instead of thinking of that Bayesian, applying the Bayes' rule, why don't we remember that a probability is also a function. Probability is a function that takes, in this case, input vectors that are d-dimensional, that's these x's here, and produces a number between 0 and 1. That's the probability that the label is 1. So the probability can be seen as a function from a d-dimensional vector to the range 0, 1. You can think of it as a function, right? Now, why not directly model this, learning this probability function as a regression problem? So, if we do that, we now expand our hypothesis space. We go from the search over all functions from the RD, the d-dimensional vector space, to -1, 1. That is the search over all classifiers. We go from that to this much richer space of functions where we are trying to search over functions that take d-dimensional vectors, RD, to the range 0, 1. And now we have at our hands a regression problem. So what this means is our hypothesis space should consist of functions that have this shape. It should all functions in our hypothesis space should take d-dimensional vectors and predict a number between 0 and 1 that is going to be interpreted as a probability. So, is the setting clear? Does that make sense? Any questions? We have transformed our learning problem from a classification problem into a regression problem by trying to predict probabilities. So one hypothesis, was there a question? One hypothesis space, and it turns out it is actually a very popular hypothesis space for predicting probabilities, is a class of functions that are all called sigmoids. A sigmoid is just a generic name for an S-shaped function, a function that looks like this, like a kind of a bent out S. In particular for logistic regression, our hypothesis space, remember our hypothesis space should consist of all functions that try to predict this probability. Our hypothesis space will consist of functions of this shape. You take this, right, this is called the logistic function. What you do is you take your input x, each function is uniquely identified by a weight vector. You take your input x and you take the dot product of that input with x, that gives you this W transpose x. And remember, the dot product can be anything, any number between minus infinity to infinity. You flatten that function. You flatten the dot product by passing it through this sigmoid. The sigmoid is simply this function, 1 over 1 plus e power minus z. And that gives you this logistic function. So you take your dot product and you take the dot product and give it to the sigmoid, and that in some sense flattens your function, and we'll look at the shape of this function and some properties of this function in a bit. And it turns out the sigmoid function has a range of 0 to 1. It maps, if you take for example, if z is at the bottom here, if z is 0, if z is minus infinity, this becomes e power infinity, so the whole thing becomes 1 divided by infinity, which is 0. If z is minus infinity, the sigmoid is 0. If z is plus infinity, this e power plus the e power minus infinity is 0, so 1 divided by 1, sigmoid is, the value is 1. So it maps minus infinity to 0 and plus infinity to 1, and it's a continuous function in between. If you want to look at the shape of this function, so that gives you the domain and the range of the sigmoid. The domain is all numbers from minus infinity to infinity, the range is 0 to 1, which means that this function hw of x perfectly fits what we want, at least perfectly fits the boundaries, the interface of what we care about. hw of x can take vectors x and produce numbers between 0 and 1. I mean, I'm not saying this is the only function of this shape. This is a mathematically convenient function. It has some interesting properties that emerge independently of this as well. If you are thinking of what the shape of this function looks like, in some sense, the sigmoid, this is like the classic shape of the sigmoid. Of all sigmoid functions have a shape. It looks like, if you kind of twist the page, it looks like an S, and it very rapidly drops down to 0 as the input to the sigmoid goes down. It very rapidly goes up to 1 beyond a certain limit, and in between it's a smooth transition. In particular, at z equals 0, the value of the sigmoid is half. So z equals 0 corresponds in some sense to, if we interpret this as a probability, z equals 0 corresponds to the probability equals half. Any questions about this? How many people have seen the sigmoid of the logistic function before? A non-trivial number. Okay, cool. If you haven't, there's no rocket science here. All I've done is just defined a function. One of the interesting things about the sigmoid, and this is just the properties of sigmoids have been, or of the logistic functions have been analyzed to death. I just wanted to bring up one property which you might find useful for your homework, for example, is what is the derivative of this sigmoid of this function of sigma of z with respect to z. So, I mean, I can take the derivative. It's just applying the definition here, and you apply the usual process of taking derivatives, and you get. In fact, let's just work this out. So this consists of two terms. So I can write this as e power minus minus z divided by 1 plus minus z times e power minus z. Oh, sorry. Looks like I can't erase this anymore. So let me just write e power. So this becomes e power minus z divided by 1 plus e power minus z times 1 divided by 1 plus. But this is exactly equal to the sigmoid of z by definition. And if you look at this part, this is equal to 1 minus 1 divided by 1 plus. Right? And this is 1 minus sigmoid of z times sigma of z. So I've written it more neatly here. The derivative of the sigmoid function with respect to its input is simply the product of the sigmoid times 1 minus. Now, one interesting way of interpreting this is if the sigmoid represents a probability of some event, then 1 minus represents the probability of the event not happening. The derivative of the sigmoid is the probability of the event times the probability of the event not happening. This is useful this comes useful in when you're taking the derivative of this in order to get the gradient step for your homework. This will also prove to be useful. This exact sort of an analysis will also be useful when we are doing just very briefly going over the backpropagation algorithm, because in some sense the backpropagation algorithm is a mechanical way of just calculating derivatives. Yes?
So I've been trying to use this in my project, and the inputs are all very large numbers.
Yeah.
Then the output of the sigmoid function is always
Is 1.
the same, so it doesn't change anything.
Yeah, this is the sigmoid is the squashing function. If you look at the characteristic of this thing, beyond a certain limit, it just flattens everything out to 1, and that works for us because this we want it to be a probability. But I think in your project you probably need a regular regression, and this might not. The range of this may not be the perfect thing. Alright, so again, this detour about sigmoids aside, we are predicting probabilities, and in the logistic regression model, we assume that the probability of the label being true given an input, and I say comma input semicolon w, that just means for a particular weight vector. So the probability that the label is 1 given an input using a particular weight vector. Another way of saying the same thing is the probability of the label being 1 given the input and a weight vector is simply sigmoid of w transpose x, which is 1 over 1 plus e power minus w transpose x. The probability of the label being minus 1 is, as I said before, just 1 minus that. And if you just substitute the definition of the sigmoid, you get e power minus x divided by 1 plus e power minus x. So obviously these two things add up to 1. But I can rewrite the second term. I can divide throughout by e power minus w transpose x, and I get 1 over 1 plus e power w transpose x. Right? No magic here. But what is interesting is these two look very, very similar except for this minus sign here. And which means we can just combine them, and notice that the minus shows up when this is a plus, and this is a plus shows up when this is a minus. So I can write P of y given w x is 1 over 1 plus e power minus y w transpose x. It's just a compact way of writing the probability function. Questions about this? And so far, everything I've done is just notational gymnastics. There's nothing deep or particularly or hopefully there's nothing particularly deep in anything I said so far. All we've seen is we want to, the only conceptually interesting point is instead of predicting a class label, we are going to predict probabilities, and we are directly going to treat the probability prediction as a regression problem. Once you jump that hoop, all that remains is picking a good hypothesis space for the regression, and we're going to pick this particular hypothesis space for the regression problem. The important thing to note is in Naïve Bayes, also we said we were going to train a function that predicts the probabilities. But what we did was, instead of modeling, so we wanted to predict P of y given x. There's a w, there may be a w, or all the parameters of the model are also given to us. Instead of learning this function, we said we're going to learn P of x given y and P of y. We learned these two separate probabilities. That's what we did for Naïve Bayes. And generally, in a lot of generative models, this is what you do. Instead, in logistic regression, we're going to directly learn this function. Does the difference make sense? Or is the difference clear? Any questions about it, or comments, or angry protests?
I have a question on the learning rate. So if we start at one end, our learning rate might not be enough to get to the...
What's the end here? And what are the ends here?
As in 1 or 0.
But we're not going to start at 1 or 0.
Okay.
Why? I didn't...
Because we usually start at a random point. And
Yeah, you can start at 0.
Okay.
You can start in the middle.
Okay.
But let's get to learning in a bit. You can keep your question and then come back to it. Are there any questions about the nature of this function? In particular, I want you to understand the subtle, possibly subtle difference that is happening here. In logistic regression, we are directly modeling y given x. In Naïve Bayes, we indirectly got to probability of y given x by learning these two separate functions. And this is like a classic difference between generative and discriminative models. In both cases, we are learning functions that predict probabilities. Okay? So, suppose you have a weight vector w. How do you predict? You compute the probability. We still want to get a classification. Yeah, sure, I've modeled this problem as a regression problem, but at the end of the day, you still need a prediction. You still want to decide whether your email is spam or not spam, for example. It's not enough if your email client tells you that the probability that this email is spam is 0.7. The probability that this email is spam is 0.3. I'm not going to delete it from your inbox because I don't know. So if you actually want a decision, there's a very easy answer. What you do is you predict the probability of the label being 1 using the sigmoid function, using the logistic model, and if that's greater than half, or some threshold that you want to care about, the most common one is half, then you say the label is +1. Otherwise, you predict the label as -1. Now, in other words, what we are doing is predicting label equals 1 if P of y equals 1 given x greater than half. But P of y equals 1 given x, this quantity is exactly the same as 1 divided by 1 plus e power minus w transpose x is greater than half. Which means 1 plus e power minus w transpose x is less than 2. I just took the inverse. Which means I can remove the 1 and this is true. Right? And I take log on both sides, you get minus w transpose x is less than equal to 0. So, by putting the threshold at half, what we are actually getting is the following decision rule. You get the input, take the dot product of that input with the weights. If this is equivalent to saying W transpose X is greater than or equal to 0. If you take the dot product, if the dot product is greater than 0, then you predict label equals 1. Otherwise, you predict label equals 0. Isn't that awesome? We started off with this fancy, lofty ideals of predicting a probability, and we end up with a linear classifier again. So the prediction with a logistic regression model does not even require, if you put the threshold at a half, we don't even need to get through this whole probabilistic analysis. You can learn your linear classifier, you can learn your weight vector, and just predict as we always have. Predict using the sign of W transpose X. Questions? So effectively what we have is yet another way of learning or thinking about it. The way we thought about linear classifiers was maximizing the, these are weight vectors that maximize the margin. In logistic regression, these are weight vectors that correspond to this particular definition of probability. Questions? Okay, so it turns out that this particular choice of the sigmoid function is not arbitrary. It has some rather interesting connections to the Naïve Bayes classifier. Let's look at that. Remember in Naïve Bayes, when I think it's been more than about 10 days, I mentioned that the Naïve Bayes classifier in the binary setting is actually a linear decision function. The decision boundary of a Naïve Bayes classifier is still linear. And I think is there like a homework question that also asks about this? There should be one. I hope there's one. So, in some sense, the way that we proved that the Naïve Bayes classifier is linear is we took the ratio of the probability of say minus to plus or plus to minus and the log of that ratio, and just by working through the derivation or through the definition of Naïve Bayes, you end up with this some W, not a particular W transpose X. But we also know that the probability of y equals minus 1 given X is just 1 minus the probability of y equals plus 1. So let's plug that in. So I'm going to take this, and this is log of 1 minus p of y equals 1 given X divided by p of equals some W transpose X. This came from the definition of the Naïve Bayes classifier. But I can take e power on both sides, so I get 1 minus y equals 1 given X divided by equals e power W transpose X. And now I can try to find the value of p of y given X, and that should give me 1 minus 1 given X equals times e power, and I can move this quantity here. I get 1 equals 1 plus e power W transpose X times the probability, and eventually what I'll get is the probability of y equals 1 given X is 1 over 1 plus e power. If I'm right, this should work out. There might be an off by 1, there might be a minus plus switch somewhere, but even this is what you'll get. So let's effectively, what happens is if you start off with the Naïve Bayes classifier, we know that the Naïve Bayes classifier is a linear classifier using in this form, or at least the decision boundary of the Naïve Bayes classifier is linear. If we directly try to model that decision boundary, what you get is a logistic function. So, something interesting happening here. The Naïve Bayes classifier and the logistic regression classifier effectively model the same, exact same posterior probability. What is the posterior probability? It's the probability of the label given the input. The Naïve Bayes classifier and the logistic regression classifier model the exact same posterior probability. The only difference is in logistic regression, what you're saying is, anyway I'm going to get to this posterior probability, might as well learn it directly. In Naïve Bayes, you're saying, I don't really want to just model the posterior probability alone, I also want to model how the data is generated, so I'm going to learn the probabilities in the way that we saw before. The Naïve Bayes classifier is a generative model that predicts this posterior distribution. The logistic regression classifier is a discriminative model that predicts the same posterior distribution. They are just learned in different ways. Questions? Yes?
Does it also overcome the independence assumption?
Yes, it does actually. And it overcomes the independence assumption. It does not have any independence assumptions here. The Naïve Bayes classifier has all those strong independence assumptions. So the reason it does not have those independence assumptions is because we never made any. When we directly decide to model this probability, we don't care about probability of x given y. Only when you care about probability of x given y do you even have the opportunity to make the independence assumptions. You don't care about p of x given y. In Naïve Bayes, you're getting to this posterior distribution through the p of x given y. And that's why we made those independent assumptions. In practice, the logistic regression classifier tends to always outperform Naïve Bayes if you only care about the decision. On the other hand, if you care about the stuff that I've said I will not be teaching, which is the EM kind of algorithm, or when you have unsupervised learning, then generative models tend to shine in that setting because they are mathematically more convenient. Any questions? Other questions? This should not be obvious. Has anyone seen this before? This should not be obvious partly because it forces you to think about discriminative and generative learning, and that's not the easiest thing to think about. If you are confused, remember the following. A discriminative classifier learns p of y given x. A generative classifier learns p of x comma y. The joint versus conditional. Discriminative models are also called conditional models. Okay? And the logistic regression directly learns this conditional probability. Questions? Yes.
Is there any advantage or disadvantage of learning the conditional probability or
So, yes, there are pros and cons of both sides. If you only care about the decision function, if you only care about the final classifier and you have fully labeled data, then in practice it turns out that conditional models tend to work better. It's an empirical observation. Most of the state-of-the-art models that you hear about are often all conditional or discriminative. Why? Because you have a certain set of parameters. You have this much capacity to model. Remember, when we talked about DC dimensions and stuff, there's this intuitive idea of a capacity of a classifier. You use the capacity of the classifier to model the decision boundary, and so that you get a better estimate of the decision boundary. It is so this conditional discriminative models tend to be better when you only care about the decision functions. It makes better use of the data in some sense. On the other hand, conditional models, or what do you call them, discriminative models, in a very loose sense, and this is by no means actual formal statement, tend to be somewhat harder to train. You have to actually run an optimization problem, as opposed to something as trivial as we saw with Naïve Bayes, literally just count. For Naïve Bayes, learning was just counting. For logistic regression, learning requires you to write an optimization. So that's one couple of points. The third thing is when you have unlabeled data, or when you have unsupervised or semi-supervised learning, discriminative learning tends to be much harder to model mathematically, because we are actually solving an optimization problem. The optimization often tends to blow up in your face. With generative models, there are mathematically very clean ways of writing down unsupervised learning. So generative models tend to be extremely useful if you are doing unsupervised learning, which is why you might see, so for example, the EM algorithm, which we will not talk about, is largely built around generative models. Some of you might have heard of topic models. Topic models are built around generative models. Why? Because topic models are the setting where you have a collection of documents and you're trying to infer which document belongs to which topic. You do not have labeled data. If you had labeled data, you could train a classifier, but you do not have labeled data, and so you have to run some sort of a clustering algorithm, and generative models shine there. So there are trade-offs, and in practice, it's some people try to be very religious about this. You only will use one or the other. In practice, whatever works. So your problem setting often dictates what kind of a model you use, and your constraints on your learning and what hardware you have, for example, and what labeled data you have often dictates what you use. Alright, so the only thing that's left at this point in terms of logistic regression is to tell you how to train a logistic regression classifier. But really, I've already told you the answer. So the logistic regression classifier is a probabilistic classifier in the sense that you're learning a probability function. But you can also train it using the probabilistic criteria. You can train a logistic regression classifier using maximum likelihood estimation. You can train a logistic regression classifier using maximum a posteriori estimation. So what I'm going to do is work out the details of both these things. The setting in all these cases is the same. We have a training set, xi, yi, and remember that the classifier is fully defined, is completely defined if I give you the weight. So the problem of learning is exactly the same as finding the weight vector. So in this case, we are doing maximum likelihood estimation. You want to find a weight vector, W, such that the likelihood of the data set is maximized. You want to find a W such that P of, I call this S here, P of S given W is maximized. We know that each of our, so what we need to do with maximum likelihood estimation is to write down this function P of S given W formally, mathematically, and at that point we have an optimization problem and we try to solve it. So we have this entire data set P of data set S, and we want to write down what is the probability of S given W. And we also know that in some sense we are assuming that all examples are IID, are drawn independently of each other. So what's the first step that you do in writing down P of S given W? Knowing that each element of S is independent. We did this for Naïve Bayes as well. Product, you write it as a big product. So I want to maximize P of the probability of S given W, but S is simply the set x1, y1, x2, y2, and so on, xm, ym. And we assume that each of these is independent. So writing down the probability of S given W, maximizing probability of S given W under the assumption that they are independent is exactly the same as maximizing this giant product. Probability of the product over each P of yi given the x comma w. Which is very convenient because the logistic regression model tells you exactly how to write down down this probability. But the other usual trick when you're doing this kind of an optimization, when you're trying to maximize probabilities, a product of probabilities, is to take logs, because we just know how to handle summations better. So we can take the logarithm of this product, we convert it into a sum. So solving this optimization problem is equivalent to solving this optimization problem. The one solving the top optimization problem is equivalent to maximizing this sum. Sum of log probability, so the log posterior probabilities. Okay? Now we can just plug in the definition of P of y given x. Remember that the logistic regression model says P of y given x is you take y w transpose x, pass it through the sigmoid, and that's your probability. And we can just plug that in. So but what we want is log of this, so we can say log P of y given x comma w is negative log 1 plus e power minus y. Right? So I can just, and this is what we want. This can go into this part, into the probability there, and so we get another equivalent problem. So what we care about is maximizing over the w's, the sum over each example, negative log 1 plus e power minus y w transpose x. Or I can write this, instead of writing max, I can also write this as minimize over w log 1 plus e power yi. Okay, so here's an objective function. What do you do with it? How do you maximize this? Okay, gradient. You can do stochastic gradient descent. This has a very similar form as the kind of functions that we've seen before. You're minimizing over the set of all vectors a function that is a sum over m things. The usual stochastic gradient descent applies. What you do is you pretend that you pick a random example, pretend that that random example is the entire data set, compute the gradient of this quantity here with respect to that random example, with respect to the weight vector, and you proceed. Right? You take a step in the negative direction of the gradient and you repeat. So in some sense, this, once you bring it down to this form, we can plug it into the same recipe that we've been using for say even SVM and for the least mean squares regression that we saw earlier. Yes?
How do we know it is convex?
How do you know it's convex? Prove it. I am telling you it's convex, try to prove it. The way to think about that is to, you know that W transpose X is convex, you basically go from inside out. Every piece of, the sum of two convex functions is convex. E power a convex function is convex, log of a convex function, and so on. So you have to basically get through, go from inside out, and you apply properties of convex functions at each step. It is convex. And that's a good question, because if you know this is convex, then gradient descent will come to the minimum. So at this point, the problem is reduced to something that we know how to solve. So instead of solving the problem, I'm going to move to a different problem. This is the maximum likelihood estimation. Just to give you a flavor of maximum a posteriori estimation, let me just quickly remind you what is maximum a posteriori. Map learning is where you have some parameters. Typically in probabilistic learning, the parameters, what I call W here, or in the Naïve Bayes, I called it H. Without loss of generality, let's just call it theta. We want to learn theta such that we want to learn theta by maximizing over all theta probability of the theta given the data set. I called it S, so I'll continue calling it S or R max. But we know this is equal to R max over theta probability of S given the theta. In the maximum likelihood estimation, we assumed that this quantity here is uniform, which means we are left with, in MLE, we want to maximize just the likelihood of the, so this is the prior and this is the likelihood. In MLE, in maximum likelihood estimation, we just maximize the likelihood of the data, which means we are implicitly assuming that the prior is irrelevant or uniform. But there's nothing that says that the prior should be uniform, because the prior gives us an opportunity to push the weight vector towards regions that we think are interesting. Okay, questions? This is just a reminder of something we've seen before. And what we just saw was maximum likelihood estimation for logistic regression. We could also do maximum a posteriori estimation for logistic regression, but we need to somehow invent a prior. We need to come up with a prior that reflects some prior belief about the weight vectors. In this case, theta are the weight vectors. So we could add priors on the weights. And one prior that we could add is the following. Suppose each weight in the weight vector is drawn independently from a normal distribution. This normal distribution has a mean at 0 and a standard deviation sigma. Sigma is just a fixed number. We're not going to try to learn the normal distribution, the sigma we could, but for now let's pretend we're not going to do that. Sigma is just a number. So every weight is drawn independently from a normal distribution centered at 0 and has a fixed standard deviation. Which means I can write down what is the prior. The prior is simply the probability of these weights, a particular weight vector existing. Which, because I'm assuming that each weight in the weight vector is drawn independently from a normal distribution, I can write it as the product over all these weights. And I can just plug in the definition of the normal distribution, you get something like this. Right? So this gives me the prior probability over the weights. Now let's think about what this means. This implicitly assumes that in the absence of any information, the weights that are most favored are the zeros, because this quantity is maximized at 0. The normal distribution has highest probability at 0, right? So what this is saying is that if you do not know anything, push the weights to 0, which seems like a reasonable thing to do. If in the absence of any information, get rid of that feature effectively.
So, I had a question. So how can we say the probability is equal to the product of all the probabilities?
Because the W is the vector that's the d-dimensional vector. The assumption here is that each weight, each Wi, is drawn independently of all the others. And by definition of independence, you get this. We keep, in some sense, in Bayesian learning, we have a small set of tools that we keep applying all the time. Conditional independence and, in some sense, a small set of probability functions and the Bayes rule. That gives you a lot of the basics of Bayesian learning. On top of that, using these basic tools, we build a lot of complicated palaces, but these tools keep coming up. Alright, so I'm going to keep the maximum likelihood estimation here just to remind you of what we did. Just we started off with, we wanted to maximize the likelihood. We said that each example is independent of all the others, and we derived an equivalent maximization problem. When we add a prior, we want to add, let's say we want to add this particular prior, we're doing maximum a posteriori learning. So we want to learn by solving the following optimization problem. You find the product of the likelihood and the prior for each weight vector, and find the weight vector that maximizes this product. Of course, I mean, if you're being silly about it, you can try to enumerate every possible weight vector and find the one, but of course we know that's not going to work. So let's plug, the same recipe shows up. We know that every example in this S is independent of each other, so we can decompose P of the likelihood into this product, just like we did for maximum likelihood. And we assume that this prior, the probability of the weight has that shape. So we get the second term here. Again, we can take logs. So solving maximum a posteriori learning, maximum a posteriori learning for the logistic regression model. In this, if you think about it, so far I have not said, if you ignore the prior, this says nothing, it has nothing to do with logistic regression. This could be any probability. The prior assumes that there's a certain W, but the likelihood so far has no connection to logistic regression. But I can just take the log, work out the details mechanically. If I take the log, I'll have a log of this term plus this quantity here, but the first term there, log of 1 over sigma root 2 pi, is a constant. As far as maximization is concerned or minimization is concerned with respect to W, it does not play a role, so we can just ignore it. We are left only with these two summations, and I can plug in the definition of P of y given x from the logistic regression model, and we are left with this maximization problem. Maximize the sum of two things, actually the difference of two things, the negative log posterior and the quantity that's proportional to the log prior. Instead of maximizing this, instead of maximizing this quantity, I can minimize the negative of that quantity. I can minimize the sum of the log of 1 plus e power minus w transpose x plus 1 over sigma square w transpose w. Does this look familiar? What does this look like?
SVM.
It looks a lot like SVM. How did we get the w transpose w term in the SVM?
Regularization.
But why? How did we get to why w transpose w? Why the norm of the weight?
Maximize the margin.
Maximizing the margins. So we've seen this, a very similar thing before. When we were in SVM land, we said the w transpose w term, remember that 1 over sigma square is just a constant. It just trades off these two things. When we were talking about SVMs, what we said was, if you're trying to, adding this w transpose w term, minimizing w transpose w is equivalent to maximizing the margin of the weight vector, and we want the margin to be maximized because it gives us better generalization. So that's the reason we came to this w transpose w. Here, when we are talking about maximum a posteriori learning for logistic regression, it turns out we have come to the exact same expression, but in a completely different way. The way we got to this w transpose w was by saying that, I don't know anything about these margins and stuff. I don't even know anything about linear classifiers. All I care about is I want to put a prior distribution on the parameters. A particular choice of the prior, which says each weight is independently drawn towards 0 in the absence of any information, turns out gives us the same thing. So this is the Bayesian interpretation of the regularizer. The same regularizer in a margin maximizing setting is saying that we want to maximize the margin. The same regularizer in a Bayesian setting says each weight has a tendency to go to 0 in the absence of any information. Now, the nice thing about this particular framework is that you know how to solve it. All you have to do is write down the gradient for this quantity and basically work through the same procedure. And in some sense, actually, your homework asks you to actually do this exercise. You write down the stochastic gradient descent for this, and the only thing that will change really from your SVM is the innermost term inside the for loop. And that's it. SGD is just one learning algorithm. Historically, the most popular learning algorithm, other training, optimization algorithms have been used. In particular, you might run into an algorithm called LBFGS, Limited Memory Broyden Fletcher Goldfarb Shannon. That's why it's always called LBFGS. Nobody wants to say the whole thing. LBFGS is just another optimization algorithm. These days, though, LBFGS is a pain to implement. I would never dream of asking you to do that in a homework. There would be a riot. So SGD has now become, stochastic gradient descent has become the de facto learning algorithm for all these things. But you might run into other optimization algorithms as well. Okay, any questions before we move ahead? So just to remind you, what we saw was we looked at the definition of logistic regression, and in some sense the logistic regression classifier is one of the two industrial strength classifiers that is bread and butter along with SVMs. Typically people say, for example me, who wants to train a binary classifier, and I really don't want to think about too much of the learning details and stuff. I just have some features. I just want to get a quick and dirty binary classifier that is about as good as it can be without too much thinking. I tend to turn to something like SVM or logistic regression, and the choice of whether I use one or the other invariably boils down to which code I have, which one of these I have more trustworthy software for. So you should be very comfortable with the logistic regression classifier, and in some sense we'll see in a minute why, just to kind of bring you back to this thought, why SVM and logistic regression perform very similarly. But before going to that, I want you to just to quickly summarize what we saw so far. We looked at the logistic regression classifier, and the idea is that instead of training a classifier, you pretend that the problem we have is a regression problem by directly trying to predict the probability of the label being 1, and treat that as regression with a particular functional form of the probability. And that functional form is you have an input, you take the dot product with the features, with the weight vector, and you pass it through the sigmoid. And it's not an arbitrarily chosen functional form. It turns out this has some rather interesting connections to the Naïve Bayes classifier, and if you did not follow that, I encourage you to kind of work out the details just to make sure that it makes sense. And we looked at training a logistic regression classifier. From the training perspective, the problem is and was solved even before we started this lecture. We have the standard criteria for training probabilistic classifiers: maximum likelihood and maximum a posteriori. And I just walked through instantiations of both these things. It just so happens that if you do maximum a posteriori learning for logistic regression, you get to this really awesome looking, awesome depending on your perspective, this very familiar functional form, where you have the sum of two terms. One of these terms looks like and is exactly the same as what we used to call the regularizer for SVM. The other term has this interesting form. So, and the other term is the summation over the entire training set, and it comes from the definition of the sigmoid function. And the whole process here is the process of learning is exactly minimizing this objective function with respect to the W. We've seen this before in a more general setting, and this takes us back to this recipe for building, other recipe for building learning algorithms, which is loss minimization. If you want to minimize, and this is stuff that we've seen before, I want to repeat it just so that we have you see it in the context of what we've seen today. The setting is we have examples that are drawn from a fixed distribution, and there's this hidden function that labels examples. We wish to find a classifier, and we wish to find a classifier that mimics the oracle. And in the ideal situation, what you'll do is you'll define a loss function L that penalizes bad hypotheses, and you can write down learning as just minimizing loss, which seems like a reasonable thing to do in life, or rather minimizing expected loss, because we want to generalize the future. But we do not know how to calculate this expectation because we do not know this distribution. Instead, what we do is we minimize empirical loss. This gives us, the goal is to find the hypothesis H that minimizes the total loss over the training set, or the average loss over the training set. Right? This is called empirical loss minimization. The problem with just vanilla empirical loss minimization is that doing this can tend to overfit. Finding zero loss on the training set does not mean that you're going to generalize. So typically you need another term in this minimization that drives the learning towards simpler hypotheses, towards hypotheses that do not overfit. This function, so we add another term that's called the regularizer to the objective, and the job of the regularizer is to penalize complexity. Now learning is no longer just minimizing loss or minimizing empirical loss, but the learning is minimizing regularized empirical loss. You have the sum of two terms. You're minimizing the sum of a regularizer plus some loss on a training set, and there's a trade-off. You can trade off between overfitting and underfitting by controlling this value C. In logistic regression, we did not have a C here, we had a C here, and we had a 1 here, but really that's irrelevant. When we talk about learning linear classifiers, there are many regularizers that exist. One very, very popular regularizer for linear classifiers is simply the norm of the weight vector. This is called L2 regularization. L2 norm, L2 regularization. There are many other regularizers. And this regularizer can be explained in different ways. One way of doing this, one explanation is to say that in the absence of any information, I want to take all weights to 0. I want to put a prior probability on the weight vector to push them to 0, and that's your Bayesian interpretation. Another interpretation for the regularizer is pushing the W transpose W to 0 is effectively similar to trying to maximize the margin, and we know that maximizing the margin is a good thing to do. So the regularizer can be, this L2 regularizer can be motivated in at least 2 ways. Okay? So that's the regularizer, but we also want, there's the other term here, the loss. The loss function should penalize mistakes, and because we're minimizing the average loss over the training set. What's the ideal loss? How do you evaluate your classifier at the end of the day? No, how do you evaluate your classifier? Accuracy. So in a perfect world, the optimal loss is 1 minus accuracy. If accuracy is high, loss should be low. If accuracy is 100%, loss should be 0. Accuracy is 0, loss should be 1. So 1 minus accuracy, which is also popularly called the error. So the error of a classifier is a natural definition of the loss. It's also called the 0-1 loss. It simply penalizes mistakes. If you have a true label y and a predicted label y prime, if y not equal to y prime, you lose 1 point. and you add up the total points you've lost. If we have a linear classifier, we know that a mistake, that is this idea of y not being equal to y prime, can be written as y w transpose x less than 0. So whenever there's a mistake, you lose a point. So this is the perfect loss that we try to minimize, we want to minimize. Unfortunately, minimizing 0-1 loss is intractable. It's NP hard. So we try to invent surrogates. If you think about it, every algorithm that we saw for learning a linear classifier, except Veno actually, it actually corresponds to a particular loss function. There's the perceptron loss, which is defined in this way, max of 0, minus yw transpose x. The hinge loss, which we saw for SVM. Adaboost minimizes something called the exponential loss. We just saw the logistic regression classifier, and remember this term that was inside the summation? That's called the logistic loss. So there are different kinds of loss functions, and if you're coming from the loss minimization perspective, effectively what you're saying is by doing maximum a posteriori learning for logistic regression, you are using the following two things. You're using an L2 regularizer plus the logistic loss surrogate for the 0-1 loss. If you are the kind who prefers looking at pictures, what we want to minimize is the 0-1 loss, this line here. This is y w transpose x here. This way. You make a mistake when y w transpose x is less than 0, so you pay a point. The hinge loss says anything less than, if y w transpose x is less than 1, it counts as a mistake and you start paying an increasing penalty as you put points on the wrong side of the margin. The perceptron loss says there is no margin. Perceptron is effectively a hinge loss without margin. There is no margin and you pay an increasing penalty. As an exercise, you can derive stochastic gradient descent for the perceptron loss. You should get exactly the same perceptron algorithm, the batch version that we saw. The exponential loss is something that it's going to take a little longer to derive, but it's another surrogate for the 0-1 loss. And the logistic regression is a different surrogate. It says that it also penalizes mistakes, it also penalizes things that are correct, but it adds an increasing penalty going all the way to infinity as you make bigger and bigger mistakes. And a bigger mistake is simply when y w transpose x is a very large negative. Alright, so to wind up, you can think of logistic regression as a classifier that does a lot of things. It's a classifier that predicts a probability for the label being +1. It's a discriminative counterpart of the Naïve Bayes classifier, which is a generative classifier. It can be trained using maximum a posteriori or maximum likelihood estimation. And another way of thinking about the same thing, it's a discriminative classifier that minimizes the logistic loss. So there are different perspectives. It's just different ways of looking at exactly the same mathematical object. Okay, so I'll wind up now. I have office hours. If you have questions, please show up. Otherwise, in the next lecture, we'll talk about neural networks.